What's up, everybody? Good to see you here. I'm making sure I got Pokemon Go off. I had a really good sandwich. My wife makes homemade granola bars with protein powder. Get some whey protein in there. Good stuff. Morbin in, ready to go. Fun times. Got all the food. Harrison is right. Office hours were beyond. Oh, Colin. Colin's here. Let's throw Colin some points. The busy office hours right now. We got Colin from Disney. Don't be cooked. You got this. Stress and don't stress. Office hours helping you out right there. Moira's practice worksheet. One thing I stand by is that you don't have to expect perfection out of ourselves. We just have to give the perfect effort. That's good right there. I do not know what that is. I don't know. Tara's got something right there. What should we cover? What should we do? Who's got some questions? We got answers. What should we do? You pick it. We do it. What should we do? Moira's practice. I should look for Moira's practice worksheet. Does Moira have it? She has it posted probably to her. I could find that. Thank you to the SI leaders who make posts. Very helpful posts. Moira right here. I'm enrolling in Moira's class. I'm enrolling it. Did she post it? Go to course. Bryson, good to see you, Bryson. Moira's the best. Her Zoom, her GroupMe, her everything. Want to be an SI? Apply here. Moira, you rock. Got the other SI leaders right there. Her canvas has it. It's probably under modules, right? Very well organized, simple modules to see right here. SI review 2 from Moira. Practice exam and answers. And she's got the videos. Man, Moira's got this organized. So let's take a look right here and review some concepts. And I'll mention some additional things, but Moira is a pro. Let's throw some 5,000 points. Put W Moira in the chat. If you see Moira, say hey to her and be like, you're awesome. And say thank you. Say you're awesome. Thank you for everything you do. So Moira's exam 2 review. W Moira, let's do this. Here we go. Okay, check the conditions for regression. What are the 4 conditions for regression? Say them out loud for me right now. What are the 4 conditions? Here we go. I'm going to take this sheet. Copy the sheet. It's on a Google Sheet. I thought it downloaded it. Paste. There we go. I saw it was on a Google Sheet, so I'm like, let me go over here. There. What are the 4 conditions for regression? What are they? I need you to know them. The 4 conditions are QQ straight enough, which means 2 quantitative variables. Straight enough. Which means a straight line decently approximates the relationship of the data. No outliers is what it says. There's no outliers. And plot doesn't thicken. I like to say plot doesn't thicken. It's just easier because that's what we want to say yes to. Great job on a QQ straight enough. No outliers. Plot doesn't thicken. Some people say plot thickens. It's just easier to say what the condition is when it's met, that the plot doesn't thicken. Some people say the outliers condition, but we want no outliers. So I like to say in the sense where I'm like, yeah, the plot doesn't thicken. It's met. And I think what I see what Moira gave you right here, shout outs to Moira because pretty sure Moira gave... Ooh. Well, that's a different residual plot, but... This is pretty good. I don't see any major issues. I don't see any major things. So the way you check the first one, how do you check QQ? Which is required for regression. So if you're watching this right now, to do the first condition, you just ask, is this quantitative? Is this quantitative? And here's the thing. If you have a scatter plot, the answer is what for the first condition? Just by virtue of there being a scatter plot, the answer is what to the first condition of QQ? Like, you can't make a scatter plot if it's not 2 quantitative variables. Do you get what I'm saying? You have to, yeah, if you have something else, you're doing like mosaic plots for 2 categoricals, or you're doing side-by-side box plots for a categorical X and a quantitative Y. So you would have different types of variables give you different types of visualization. So the visualization is dictated by the variable type. Morbin in right there already. Why is Mubot Morbin in right now? I don't even know. He's got a mind. Anyone Morbin? Who knows? Okay. So with this right here, is he possessed? The next condition is straight enough. To check straight enough, you ask yourself, does this line mostly cut through the center of the data? As in, if you look around the line, do the points go about equal like, are they somewhat, it's like a slice of pizza. It doesn't matter if the slice of pizza gets thicker. It matters if the line cuts through the middle of it. Does everyone understand what I'm saying? I'm trying to make this very clear. that if your data goes like this, is it straight enough? Yes or no? Is it straight enough? Yes or no? Type yet Y or N in the chat. Is it straight enough? Type just Y or N. Yes. Because it's cutting through the center of the data. The center of the data is where the line is at. That's the center of the x's, is in the center. Now, there is a huge condition problem with this one, and it would be plot doesn't thicken. This one has a big problem with the plot getting thicker, a huge problem. That'd be a perfect example of plot thickening, so that would fail that one. This one is pretty all right on plot thickening. It's not so bad. You really want to look at a residual plot for this. It's not bad. A little nonlinearity there. This is a pretty darn good regression, and the no outliers is checked simply by seeing there are outliers or not outliers. I think this is a separate plot than the other one, so you just see if there are outliers to see that. Down here below is a residual plot for the regression model for no. Oh, it's a different model. Good. I thought it was. I was like, that looks like a different one. And so here in a residual plot, you can see that there's big outliers, and you can also see that the line is not being followed because this is the linear model. So there's a problem with it going nonlinear. Yeah, we should have it very obvious. Good question, Dawson. Yeah, like this one right here is super duper obvious. The plot thickens. And I do want to mention just really briefly, which of these graphics 1, 2, 3, how many of them fail plot thickening? How many of these graphics fail plot thickening? How many of these graphics 1, 2, 3 fail plot thickening? Or which ones? You can give me the numbers if there's more than one. 1 and 3. So it's not just that the plot gets thicker, it could get thicker in any direction. You want the plot to have the same thickness throughout. So you want it to have about the same thickness. So it's not, people say, but the plot got thinner. And it's like, well, the plot doesn't thicken in either direction. You want what is called homoskedasticity, which means same thickness. You do not want heteroskedasticity, which means differing thickness. Just very briefly on that, and we'll just try to have as many times as we can. Would you include the rest, based on the plot above, what can you conclude about the regression model used for the data? It's got some big outliers. Does everyone see? I can see right here for the model above the big outliers that are huge residuals. In a residual plot, I'll throw you a few questions right here. Try to answer them in the chat. The sum of the residuals is always equal to what? If you add all the residuals, the sum of all the e's, which are the residuals, is equal to what? We'll do a few questions here to see if you know about residuals. If you add up all the residuals, and you think some are above the line, some are below, some are above, some are below, some are above, some are below, it'd be 0. The sum of all the residuals is equal to 0. If a residual is positive, what is bigger? If a residual is positive, what is bigger? So on your formula sheet, you have the equation for residuals. The equation for residual is given right here. It's actual minus predicted. And so you would write the equation residual equals actual minus predicted. I also write this sometimes as R equals A minus P. That's not actual statistical notation, it's just a memorization. A residual is how much we miss by. I'll do a question here, Tara, on that too. Good questions, Tara. So a residual is how far away a point is away from the model. And if a residual is positive, it's where to the line, the actual. If a residual is positive, thank you, Nancy. If a residual is positive, it's where to the line. It's on the review sheet. Can be found on review 2. It's above the line. So let's see if you can solve the following question. Are you ready? Which Moira kind of has right here. 1. The test predicted score. Okay. So your predicted test score is equal to 60 plus 2 times hours studied. And so with this, I want you to do the following. Your friend, or would you rather have a positive or negative residual? What would you rather have? And I think about what it means. Would you rather have a positive or negative residual? Would you rather have a positive or negative residual? Positive. Because that would mean you did what? Just explain to me, like, I'd want a positive residual because that means I did what? You're very correct. I want a positive residual. If you have a positive residual, you would what? Scored higher than predicted, right? You score higher than the model predicts you to be. Because that's what a residual is how far away we are from the prediction. You scored higher than you would expect with how much you studied. So now we say the following. Someone studied 10 hours and had a residual of 30. What did they score? It's residual of 20. Sorry. There we go. Someone studied 10 hours and has a residual of 20. What did they score? E stands for residual. Great job. And Tara, thank you so much for all those questions. And Kai, 5,000 points. Keep asking those questions. Dawson was like this. Dawson was just on fire with that. Dawson. Look at what Dawson did right here. Dawson went and said, we plug right in here 10 hours. That is the X right there. You can also mark your notation. They studied 10 hours, and this is E. So we would plug in the X value right there into the equation. Yeah. Dawson, is this very useful for a lot of what people do with just... the linear model is like one of the most useful models across all disciplines. Whether you're doing sociology, psychology, nutrition, kinesiology, you name it. Everyone uses linear models. It's the bread and butter of analytics. And so this is their predicted score. So what we would have right here is we'd have a model, and you would go here to where there's 10 hours of study, and that's where it would be 80. Even forecasting labor for Disney. You got it. I like... So this is their prediction. Does that make sense? This is the predicted value. If anyone doesn't know, put some W. Collins in chat, 5,000 points. And Dawson's got to come in there too. Cullen works at Disney right there. Cullen, sorry if I ever mispronounced Cullen. Works at Disney, and analytics is everywhere. Disney uses analytics all the time. It's what makes that in Pixie Dust makes it a magical kingdom. That in Pixie Dust. It's how a lot of our labs worked. We typically took out a lot of linear to understand things worked. Yeah, all of relationships are linear. Not all, but linear is a very good model. So this E right here, this E is equal to 20. So you literally just go right here, and you could solve the equation if you wanted, where you could say E is equal to actual minus predicted, and so you'd get 20 is equal to Y minus 80. And what do you think Y is equal to? This is just another way to solve it, because you can also visualize it and be like, oh, well, they scored 20 higher than predicted. So if you know what a residual is conceptually, you can solve it too with the concept, exactly 100. And you can just solve the math by doing plus 80 on this other side and algebra it out. But then the visualization over there, if you know they're 20 higher than predicted, also solves it. Moira's got some questions. Calculate the residual and state if our model is under or over predicted. Calculate the residuals, though. Predicted value 17 and observed value 25. But is that for this? Oh, it's for the previous. Sorry, let me grab the previous thing. Wait. Oh, she's saying you predict 17. So you'd predict 17 and you observe 25. So the observed is the actual, which is Y, and the predicted is the Y hat. So is the model under or overstated? 100 was the actual score. 100 was the actual, and 80 was the predicted. Kai, good questions. And keep those questions coming. This is the predicted, and the model under-predicted them. Yep, the model under-predicted. So the model under-predicted. Predicted value is 11. So that'd be down there. And the observed value is 5. Well, now we're on. The model over-predicted. So there is the observed value of 5. And predicted value is still, if you trace over. So now the model over-predicts. And think, because we predict over what they had. And let me know if there's any more questions. Kaya, really good stuff. There's the previous solve right there. And we're just going to keep rocking and rolling. So there's a lot to cover, and keep it up. You don't even have to use the residual equation. You can just write them all instead. Well, that's not quite an extrapolation. Good question, Nancy. Let's talk about what an extrapolation is, and then we'll do negative residuals. So 2 questions in the chat. What is an extrapolation? Well, we have a model up here from class. We, today in class, predicted the price of a car based on its mileage. When would this model be extrapolating? When would this model be extrapolating? For cars, what? When would this model be extrapolating? So when would this model be extrapolating? Does anyone have any ideas about when? You could use about above. Nice job, Rory, right there, because that is outside the bounds of the x's. When there's no data, it'd be after that point, and about 120,000. Extrapolation is making predictions beyond the x space of your model. Your model only has data between this and this bounds. So you really only want to make predictions within the x space of the model. How far does your x's go out? That's where you know the model and know the data. Now, if we extend our model out to far out here, it gets kind of wacky and talks about negative prices of cars. And we can forecast, which is a nice way to call it extrapolating. So outside the X bounds is when we extrapolate. So I could say, what do you think the price of a 200,000 mileage car is? And I'd say, well, this data doesn't really have the ability to predict for that car because it would have to extrapolate. We don't have X's around that. Extrapolation is when you make predictions outside the X space. You can extrapolate in the negative, but it doesn't really make sense because you can't have negative mileage. But extrapolation can happen on any bounds. Like if we predict the price of cars based on the year, where would we be extrapolating on price of car with years? Where would we be extrapolating on price of cars with years? It tells you when this data is created. Well, I'll make it a little easier. About, you can say about, because then I'll know. Where are we extrapolating? Yeah, past 2021. Yep, past 2021. But also, so Dawson, you're right. You would be extrapolating to go past 2021, but also what? And then there's the negative residual question, which I'll cover too. But also what? Before right here, for this point. Sparse data back here, which kind of creates problems too, but before 2003 or so. Do you see this point right here? Before that point. So whatever, you can hover over and it tells you before 03. So these are the bounds of your x's. There you go. And if you go outside those bounds, you are extrapolating. Your model only really works correctly-ish within 2003 to 2020. Predicting outside those bounds is not a good idea because your model is going to have to extrapolate. You can always extend the model out, but you are extrapolating your model to where you don't have data, and we would not think you only should predict within the X space of your model. If you go outside that, you're extrapolating your model. So the points around the outliers, good question right there. An outlier is defined by having a big what? Who can finish this sentence? An outlier in the bivariate sense would be defined as having a big what? The biggest outlier is going to have the biggest what? Think of an R word. Outliers are defined as having a very large, which it might be, this one right here is pretty big. Outliers are defined as having big whatses. That one's pretty darn big. That one's pretty darn big. Residuals. Outliers are defined as having pretty big residuals. They're far away from the bulk of the data. And to see all the residuals at one time, we can simply go here and plot the residuals. By plotting the residuals, I can see if I identified the big outliers. And you can see I did get all but one. That one was pretty darn big too. And negative or positive, you can be a negative outlier or positive outlier, which brings us full circle back to that question about negative residuals. So there can be a negative residual. Yes, Abby was right. Let's say you're going to buy a car. Do you want, when you predict the price of your car, and you know everything about this car, you're not being tricked, it's not a lemon. You know everything about this car. You are 100% certain. You've had it tested. Your mechanic has come through. Do you want a negative or positive residual? You're about to sit down and do the pricing. They hand you the price sheets. You want to see a negative or positive residual. And you know, they're not tricking you. It's not going to be you want a negative or positive residual. Negative. So don't worry. Good. And so why negative? Let's look at why negative. So with this example right here and why we'd want a negative residual, predicted price is equal to, and let's say right here, we're just going to do a simple regression. Let's go 15,000 minus 1. Here we go, 0.5 times mileage. Okay. The car has 200 miles on it. No, 2,000 miles. I want to do 2,000 miles. The car has 2,000 miles. Predict its price. It has a residual of negative 4,000. How much does it cost? So if you get a problem like this, start marking your notation because the formula sheet's going to help. So don't worry, David, 5,000 points. Keep up the answers. So I'm going to start marking the notation, see if you can solve it while I do this. Predicted price is equal to B0 plus B1x. And then we have the car has 2,000 miles. What should I mark for this? The car has 2,000 miles. What should I mark for that? What is the car has 2,000 miles that I'm about to predict for? That is the value of what in notation? Yep, mileage. Nice job, Darius. It is X. And we're going to predict Y hat using X, and it has a residual of this. So that is your E when you do it right there. It's the actual X. That is true. And then we're asked to solve for how much does it cost, which is the Y. So we are solving for the end. How much did the car actually cost? So these are the solves throughout this. The car has 2,000 miles. That is its X. The car has 2,000 miles. Predict its price. What do you predict the car to cost? So how would we predict the price of the car? Go ahead and do that right now and see what you get. We're just going to take the model and we're going to subtract off 0.5 times 2,000. And the predicted price of the car is what? 14,000. Boom. I predict the car will cost $14,000. So the residual is 4,000. Now, if you know how to think about residuals, what residuals are, this is the negative space, this is the positive space. Explain to me this residual in context. What does the residual mean here? So what does this residual mean? What does that residual mean in context? Just talk to me. And Dawson's already got it. Nice to have Dawson. It means the car costs 4,000 less than predicted. Because if it's the negative, the prediction is higher because you're below the prediction when you're negative. So it costs 4,000 less than predicted, 4,000 cheaper than expected or predicted. Great job. I think once you do the ARM thing, if I see people doing this on the test and they're like trying to figure out, I'm good with that. You're like, wait, here's my line. Is it above or below? Negative residual, positive residual, zero residual. Good way to remember it and remember what space is. If you do it a few times, you just start to remember it in your head. And so we would write here E equals Y minus Y hat if we're solving it out traditionally. Doesn't hurt to show a traditional solve here. Negative 4,000 equals, and we want to solve for Y minus 14. There you go. And if you notice right here, if you add the numbers to the other side, you'll get 10,000 equals Y. Just algebraing it out. So good stuff right there. The negative residual means it's less than predicted. The positive residual means it's more than predicted. Be careful. The positive residual means the model under-predicted because the model would be under it. Okay, let's rock and roll. Who's having a good time? Is it just me? Today's been a really great day. I have a feeling today's going to be a great day. You're welcome. Have really good questions. We got some interpretation stuff here with height and weight, some of my favorite models. Olivia and Darius having a good time. So much fun. So much room for activities. So we first need to identify B1. What is B1 here? The equation is predicted value of Y equals B0 plus B1x. Just tell me what B1 is. It is the slope. Tara's got it right there. And so the slope is going to be that value. The intercept is going to be this value. And the x variable is weight, which we see here. And you notice Mubot's already putting the slope interpretation in the chat. Try writing it out right now. And Kara, great work right there. So try writing it out because you're going to see that all you do is just plug in. If this is your first time trying to memorize it, remember you'll say 1 twice. For each 1 unit increase in x, we expect y to increase or decrease by b1 on average. For each 1 unit increase in x, we expect y to increase or decrease by b1 on average. And you won't say increase or decrease. I see people do that on tests. I'm like, no! So what's the interpretation of the slope here? For each 1 unit increase in weight, we expect height to increase by 0.07 on average. Great job, Darius, right there. So try writing it if you're in the chat right now. Try saying it. Because when you get to the test, you will be writing these out. There are 12 points on the test. 12 points on this test. There's 4 questions, 12 points. So how about that intercept? How about the intercept? So the intercept is going to be when x is equal to 0, we expect y to equal b0 on average. So what's the intercept interpretation? When x is equal to 0, we expect y to equal b0 on average. Throw a little on average on there. I didn't put it on there, but I don't think we need it. So what's the intercept interpretation going to be? Which it doesn't make sense. You should comment if it's logical then, because you'd be like, that really doesn't make sense. Like, I don't know about that. You throw a little like, throw the logical thing on there for me. So if you're doing this interpretation right now for practice, throw the, is that logical? Does that make sense? Because you say, if you see what Mubot's pinned right there, when weight is equal to 0, I don't think someone can weigh 0. We expect height to equal 56.3 inches. Who notices I'm just plugging in numbers? When weight is equal to 0, we expect height to equal 56.3 inches, because that's B0. And also, if you mathematically solve it out and you plug in 0, you would see, if you plug in 0 right there, that solves to 0, and you just get the predicted value of y hat when x is equal to 0. So this is logical. You would just comment at the end. So the perfect answer would be, on an exam, the perfect answer would be, I would just say the interpretation start, I would say, when weight is equal to 0, we predict that somebody's height will be equal to 56.34 inches. This is illogical because you can't weigh 0 pounds. That would be the perfect answer. Throw that a little like, when you just think over it, be like, yeah, you can't weigh 0 pounds. This is illogical. You just throw that last little bit on there, Dawson. Does that make sense? When weight is equal to 0, when weight is 0 pounds, we expect height to be 56.34. Great job. You don't want to say will be. You just want to say predict or expect. Like, those are keywords right there. And then you just throw on a little like, that doesn't make sense because you can't weigh 0 pounds. I don't see how that works. It doesn't make sense. One last thing to interpret right here. What is the last thing to interpret? Tell me in the chat. What is the last thing to interpret? Last thing is what? R squared. Yep. So how do we interpret R squared? How do we interpret R squared? Newbot's got it in the chat. Who can do it? Remember, practice. You're going to be writing it out later. Who can do it? Blank percent of the variation in y is explained by the variation in x. Newbot's just spamming the chat with it. Blank percent of the variation in y, I'm just going to hit my table more, is explained by the variation in x. And you do not talk about it like correlation. So all you do is just plug in the numbers. And you times by 100 when you do the percent. So who's got it? I'm going to let you try to do it, and I'll answer it in like 30 seconds. We'll keep going through questions. 36.1% of the variation in height is explained by the variation in weight. Dawson, just that's all there is to it. That's it. Do you have to find R squared? If we gave you correlation, you would square it, and we'll pretty much give it to you. It's pretty much just giving an output. It's like, here's the R. I think for the last ones especially, just give it. Good question right there. 36.1% of the variation in height is explained by the variation in weight. Yep. And remember, x does the explaining. So if you're trying to remember where did the x and the y go, blank percent of the variation in y is explained by the variation in x. Does everyone hear like I'm accentuating that? Blank percent of the variation in y is explained by the variation in x. So we are saying that x does this much of explaining. Is this model statistically significant? The statistical significance of the model is found by looking at the p-value of the slope. We talked about this a lot in class. If you ever hear statistical significance, that means look at p-value, and you want to look at the slope. Y is explained by x. David, you got it right there. Here is a model with an intercept equal to 0. In this first model, the intercept is equal to 0. In this second model, slope is equal to 0. Which of these would you want to be study time and test score? If there was a relationship between study time and test score, would you want to see model A or B? Which of these would you want to see? The model with the intercept equal to 0 or the model with the slope equal to 0? You'd want to see model A because there's a relationship. So we don't look at the intercept to see statistical significance. The intercept, it doesn't matter. In a lot of senses, it doesn't matter. Well, so Darius might say B, and maybe why? Because if the answer was B, it wouldn't matter how much you study. You'd be like, well, I'm going to make an 80 no matter what. I don't need to study. But in A, there looks to be a statistically significant relationship that the more you study, the better your exam grade. So we look for the slope's significance right here to see if the slope, and Darius is out thinking the question. I was like, I think what am I doing to say that? We look at the significance of the slope. A non-significant slope is more flat. A significant slope is more sloped, and it's less than 0.05 right there. And Adeline and Cooper, shout outs, 5,000 points. Adeline also for asking. The p-value is statistically significant because it's less than 0.05. Thank you, Cooper, answering the question before I could. Love it when people are answering questions. Remember, swing by any office hours. I'll cover any question. Who watches office hours later in the day? And maybe you're like, man, I wish he had done this question. I wish he had just put this in the video. Just swing here and ask. I'll do it. I'm here. I'll be here. We'll try to do more office hours, do a bunch. But just swing by, ask a question. I know a lot of people swing by and ask questions. I love it. And we'll do it in the video. What does it mean for something to be statistically significant? We found a p-value what? We can put a few facts here. The p-value was what? Just repeat it again. We just said it a second ago. Cooper said it. I don't think there's too many. Less than. Don't worry, Tar right there. Good review. P-value was less than 0.05, which means unlikely by random chance. Does it make sense? Unlikely because by change, sure. Unlikely by random chance. Darius got right there because when we say unlikely, does that sound like a high or low probability? When you say something is unlikely, does that sound like a high or low probability of something occurring? A low probability. Now, if we were to look at cheeseburgers and test score, like I say, how many cheeseburgers you eat the night before the exam, which shouts to Cookout, really good stuff at Cookout. I used to get like a tray for $5. Now it's like $50. Which graphic do you think you'd probably see for cheeseburgers you eat on the exam and your exam score? So this is cheeseburgers you eat and your exam score. Which graphic would be the likely graphic to see? Which graphic would be the likely graphic to see? Probably graphic A. Now, there is a little bit of a negative slope. I tried to correct it, so it's a tiny little bit negative. But those variations in the line are probably just due to what? Like that little difference right here between the people who ate more cheeseburgers and scored a little bit lower, those differences would be likely by random chance. And if you saw this, you'd be like, man, I need to eat some cheeseburgers because this is such a strong relationship. It looks unlikely by random chance. Does everyone understand here that when you say something is unlikely by random chance, you're saying you think there is something going on here? I think there's something about eating those cheeseburgers in graphic B. I don't know what it is. Maybe Cookie's having an all-night review session. Like there's a lurking variable. Lurking variables are variables that are not included in the model. Like if cheeseburgers are somehow connected to studying, like a Cookout has a study session, then the fact that you went to the study session at Cookout is actually what's doing it. It's not the cheeseburgers. Did everyone hear what a lurking variable is? Lurking variables is not your X, not your Y, it's a Z. Most famous example we have about lurking variables are shark attacks and what else? The most famous variable thing we have with shark attacks is what else with lurking variables? Shark attacks and what's? Shark attacks and what else? Reviewing from class. Ice cream sales. Because is it a fact that when we see more shark attacks, there's typically more ice cream sales? Yes. When there's more ice cream sales, there's typically more shark attacks? Yes. The lurking variable is a variable you do not see because it's not included. I call it a Z variable. And it is what is kind of impacting both. And great job right there, David. It's summertime. Another famous example we have would be TVs and life expectancy. Do you think it's a fact that people who own more TVs live longer? So TVs and life expectancy. Do people who own more TVs typically live longer? And we already have the answer. It's probably money. Money buys TVs. Money buys health insurance and things like that. So it is a fact that usually if you have more TVs, you live longer, but it's probably due to the lurking variable. A lurking variable is not your X, not your Y. It's like where we see, wait a minute, people eating cheeseburgers did really well in the exam. And then we find out, oh, Cookout did like a huge study session, or Cookout said if you buy enough cheeseburgers, we'll give you the answer to the exam. So they're cheating, don't cheat, Cookout. We did R squared, we did B1, B0. A lot of regression. We'll continue down because let's do a different one. I'm trying to go to a different type of thing. A lot of predicting. Oh, Kermit and Gonzo. I love that. Okay, here we go. Let's do sampling. You ready? Who's ready? What is the best thing I do for full refresher for the test? Yeah, I'd watch the videos, practice with us here, come up with the questions. This was all on regression, basically. And now we're about to do sampling, which we haven't done yet. So get ready. I'm going to mark this in the video right here for Moira's review. And just try to write as many questions as you can. Moira's review. And here we go. Let's do it. Sampling chapter. Okay. So what you need is a clear definition of all of these. Simple random sample is done howly. Let's write clear definitions. You ready? Simple random sample is done how? Give me some ideas for this. Step 1. What do we do for simple random sample? Any thoughts? What do we do? How do we do it? It is. How do we do a simple random sample? I like that, Cooper. Yeah. Everything gets a number. Just pick random things. It's random number generation. It's just you say, hey, let's pick 50 UT students, and you just pick 50 randomly. It's called simple random sample. It's kind of the first one we ever do. Everything gets a number. Everything has an equal chance of getting picked. Everything has equal chance of getting picked. It's really good. Sometimes it's hard to do, but simple random sample is a very good way of doing things. Stratified. Here we'll do systematic first. Because stratified and cluster where people start to get confused. Like, I swear, I hope this semester we do better, but some semesters is like a 50-50 guess between those two. So systematic, easier one again. How do we do systematic? There's kind of a preliminary step to this that's...
It doesn't matter!
That's kind of every kth observation, yeah. Start at a random point, select every kth observation. There we go. That's how to do it right there. Every kth observation. And then how do we do stratify? Now, there's people get stuck. How do we stratify? Boom, Dawson on fire. Nice answers, Dawson. Great answers today. Everyone good answers. How do we stratify? Look at your notes. Write it down if you don't have it. Knowledge of difference. Kaya right there. Acknowledge a difference you're going to sample with respect to. Do a simple random sample. It's not a multi-stage. You have to do a simple random sample within your strata. And we'll see some examples here. Let me put this to a new page right here. There we go. So we can keep it all on one page. And then cluster sample. What's the steps for clustering? What do we, in good work. Good job, Kai. I think get your notes out or good memorization. So what is, yeah, exactly. Things are in random groups. So this is not a difference you're acknowledging. Things are just in groups. Things are in random groups. Take however many groups you want. Do a census. Yeah, that's cool, right? Exactly. A census on the groups. Take data on everything in it, which is key. The whole idea of the census is key, which gives away a lot of the questions. So the first thing right here, every 70th person is chosen in a survey to be done. What is this? It says every 70th person. So what method? Try to get on screen, but you can see all the methods. Very simple, systematic like that. You get one like that, you're like, yeah, that's systematic. The next one says every chair in a room has a number, and a random number generator is used to select 30 unique seats. This would be what? So we're going to try to put it on the screen so you can see it all. That's simple random. You see, like, everything gets a number, just pick randomly. So very, very clear. These are great worded. I mean, it's very clearly simple random sampling. You randomly select a dormitory on campus and you survey everyone who lives there. Okay, so let's do a poll. Okay, so, oh man, everyone's so quick. How easy is it with the definitions like right here? With the definitions right there. You're fine. With the definition on the screen, I can't even get the poll up fast enough. Because you're like, well, wait a minute, they say do a census. So you can see very clearly with the definitions on the screen, it's like, well, that's easy. You divide, I wish you did some repeats or tricks in here. You divide a classroom into 4 groups and randomly sample students from which in each group literally follows the definition. And I love Moira's great, like writes excellent stuff. I would say based on class level at UT. Usually we try to specify like this, and this is very much stratified. So acknowledge a difference within the group, like stratifying based on class level, and then you randomly sample within each group. So you do a random sample within each strata. It's not a multi-stage. Yeah, cool. And this is good right here. Really good practice. So let's do this. What are we going to do a survey on? Give me a topic to do a survey on. What should we survey people on? Do it on, like, I don't want to say it. I give answers, and then it's like everyone wants to do the examples I want to do. Favorite ice cream. We could do favorite ice cream. Let's do favorite ice cream. Ooh, I like this. So how would voluntary response bias come into play right here? Voluntary response bias is when people who volunteer have differing opinions than those who don't volunteer. And maybe we're having people try ice cream, and we ask people, are you lactose intolerant? So you think people are going to volunteer to try ice cream if they're like, does that make sense? Voluntary bias is people who volunteer to take the survey often have strong opinions and are not representative of the population. We like the real ice cream lovers, strong opinions on ice cream. And then like they're saying like, I'll do your survey. And it's not a random sample then. It's a bias to get voluntary people to do it. Thank you, Darius. You're cutting down on the voluntary bias for us. Convenience sampling is getting what? I think it's convenient. Always try to use the word to understand what the definition is. Voluntary bias is people who volunteer typically have stronger opinions than those who don't volunteer. Getting the first you have access to, getting people we have the easiest access to. Going to freshman orientation to give ice cream samples to rate. Like, man, we need, hey, there's a freshman event going on today. Let's go to that freshman event and just get everybody there. Well, that's freshmen, like, nothing wrong with freshmen, but like, if you want to know what UT students think about ice cream on campus, you don't just go to the freshman event. You got to go to you got to get a random sample of UT students. So you would have actually done what? If you just go to the freshman event, you've actually introduced what? You've undercovered. Mm-hmm. So we actually, through convenience sampling, created an undercoverage bias because we only talked to freshmen. UT Creamery, shout out UT Creamery. I need to, maybe I should swing by there going home and just bring my wife home some ice cream. That'd be nice. Leaving out or underrepresenting. Good job, Kai, right there. Wouldn't be completely leaving out. There's not enough like underrepresentation. So you've undercovered them in your survey. Non-response, when people who don't respond differ in their opinions than those who do respond. And you see this a lot, especially with controversial things. Like anyone who's willing to usually talk on a controversial topic, that might also go into voluntary bias. But you're like, well, the people who are not talking on this topic are probably differing in their response than those who do talk. And what do we mean by this? Like, just think you decide to do a survey on, so you get, it's kind of intertwined with voluntary bias because the voluntary is the people with strong opinions respond to you, but it could also be, you could also get it not because of strong opinions. I'm trying to think of a good example. Like in our ice cream, oh, well, yeah, who's going to not take our survey? Who's very unlikely to take our survey? In the ice cream survey, who's very unlikely? We say we got an ice cream survey, and someone's like, oh, I love ice cream. They're like, oh, that's voluntary bias. And who's probably not taking our survey? Like, they're like, I'm not going to take your survey. Yeah, people don't like ice cream, lactose intolerant, or maybe like allergic to milk products too. Like, does that have milk in it? You're like, yeah, it's ice cream. They're like, I'm allergic to milk. We're like, that's okay. But so if somehow we're asking people in the survey questions, like, are you allergic to ice cream products? We could say like, hey, we did a survey on ice cream at UT and no one's allergic to ice cream products. Well, it would be because of what? What would be the main reason our survey at UT where they tried ice cream and told us what they thought, and we found out through the survey also because we asked some questions, no one's allergic to ice cream products. That would be due to what bias? You would say that's due to what bias? So you found out, it's kind of intertwined a little bit with voluntary, but it would be non-response, where the people who didn't take our survey, because the people who are allergic to ice cream, and we say you have to try the ice cream, take the survey, they're like, I'm allergic. And you're like, well, I guess you're not taking my survey. So the people who don't respond to the survey, like don't take it, like don't give responses, they differ fundamentally. Does that make sense? Like we're like, we found out no one's allergic to ice cream. Well, your survey was biased. It had non-response because it didn't include the people in it. Like they were not part of it. Does that make sense what non-response is? I think this one can be one of the harder ones to understand. Yeah. How about this response bias here? When the survey or the person giving it creates a bias in the response. We say to them, try the award-winning ice cream that was voted best ice cream in America. It's from the UT Creamer, if you didn't know that. Give it a rating now. Okay, so what should we say to them instead, rather than we weren't voted best ice cream in America? I mean, we should be, but what should we be saying to them instead of try the award-winning ice cream that was voted the best ice cream in America? Okay, what's your rating for it? You should just say, how do you rate this ice cream? The whole thing before that is biasing people. You can actually get what's called a good surveyor response and a bad participant, good participant response, where they'll try to like be like, oh, you think it's the best? I give it a 0. Or someone be like, yeah, it's the best. You said it is 10 out of 10. People will do things because of this. Yeah, so you're biasing them. It creates a bias in the response. It pushes them towards directions. Like someone has what they think about the ice cream, and then when you try to word a question to push them in directions, you're inserting response bias because you're trying to direct the response. Does that make sense what response bias is? Your goal in putting this preamble for the question is to create a bias in their response. You're trying to get them to say, oh, it's so good. I think it's great. And you're like, man, everyone loves our award-winning ice cream because we said it is. Yeah, don't do that. That way of doing that. Any last questions on these? That covers a good bit of this chapter. This chapter is mainly memorization. The things that were not mentioned here are you should know what a sample is, a population, a parameter, a sample frame, and that's about it. The sample would be what in our ice cream example? The sample would be what in our ice cream example? What would the sample be in our ice cream example? What is the sample? I want statistic. What would the sample be? The people that responded. The people that responded. People just tried the ice cream and give rating. How about the population? Well, we're doing this creamery for UT students, so a lot of times the people or group we want to understand UT students. If we're trying to understand UT students theoretically, like we're like, well, what do UT students think about the creamery? So all the people or whatever it is that we're trying to understand. So the population is what we're interested in. Sometimes it's called the population of interest. So what is the parameter? What is the parameter? The parameter is what? Who knows what a parameter is? Often called a population parameter. So can be called population parameter of interest. This is what? What was the parameter of interest for this study? I listed it above. Well, it's estimated by the statistic. What was the parameter for this study? What was the parameter of interest for this study? Parameter. It's called the parameter. It's the quantity or thing we want to know about the population. It's whatever value we're trying to understand about the population. The parameter of interest was what for the population? The population is UT students. It could be ice cream flavor. It could be ice cream flavor. Check above. Check above. Erica, good answers right there. It could be ice cream flavor, kind of, sort of. Rating. How they rated it. That's going to be some numeric quantity value, the rating they give the ice cream. Or how many people like certain ice cream. That could be it too. Some sort of numeric value. The statistic is a sample statistic known or comes from samples and is used to make inferences about the parameter. It is our best guess estimate of the truth. So the parameter is the truth for all people. So the true rating all students would give the ice cream. That's what the parameter is. We want to know what all students think about the ice cream. So our best guess is what our what thinks about the ice cream. Finish this sentence. We want to know the parameter of interest, which is what all students think about the ice cream, what the rating they would give. So our best guess is the statistic, which is the what. It would come from our what. So the best guess of what all students think about the ice cream is how our what rated the ice cream. It's our best guess. The sample. Does that make sense? Like, well, the sample rated this ice cream the best ice cream. So I would guess that students probably like this ice cream the most. Now, we're not saying they do. We're saying I think that from my sample, I've got an estimate of the truth. So the sample is used to make inferences about the population, like we call it inferential statistics, which is key. The sample frame, if we go to a big UT welcome event, what's the sample frame? We're going to go to a big UT welcome start of the semester event. We're going to do this ice cream sampling it's going to be all students invited. So, yeah, kind of Harrison. Good to see you, Harrison. It's going to be people or things we have access to sample. The frame by which we are sampling from. Think of a frame, and you're going to pick things out of that frame. So, students who attend the event where we give out ice cream and have ratings. So you walk by. Okay, same. Okay, so you're all UT students here. Let's make that clear. We want to understand UT students. You walked by the tent with the free ice cream and didn't try any. So you're at the event where they're going to have free ice cream, but it was like so busy. You were busy and didn't have time. Okay. So, Harrison on fire right there. You're right, Harrison. So you're in the population because we want to understand what you think about the ice cream. So you're a person we want to understand. You're part of UT students. We want to understand you. You're in the sample frame because you were at the event. So we could have theoretically sampled you. Does that make sense? It's not that you're like, oh, it was too busy. Maybe if you had walked by at a different time, the tent would have been less busy. You were at the event. So theoretically could have sampled you. We could have we could have sampled you somehow. But you're not in the sample because we don't have data on you. So the answer is, do we want your data? Yes, you're in the population. We want your data. Could we theoretically have sampled you? Could we have sampled you? And then this is, did we sample you? We could have if like times were different. You know, it's like if you go to the library and take surveys, anyone in the library could be in your sample. You just had access to sample them. They might give you non-response bias. You kind of give us some non-response bias there because you're like, I don't have time for this. Well, that's non-response bias. We're not going to know the opinions of, Dawson already said it. Right. Why do I even teach? Dawson's got the answers. Dawson, you're right. It was you did not respond. And if there's something about like a club that's there that doesn't have time to try the ice cream, like some club is setting up things and everyone in that club can't try, and it's like the We Hate Ice Cream Club, then theoretically, if there's Dawson, you figured it out. That person kind of gave some non-response bias because they were like, yeah, it's not that everyone you don't get gives non-response bias. Is there something inherently different about you? Like maybe seniors are too busy, which creates an undercoverage due to the non-response bias. That way we don't get enough seniors. Like seniors go to the event, they're like, I don't have time to stay here. And they're like, but you got to try the ice cream. They're like, I don't got time. I'm a senior. So things can lead to other things like people not responding, like seniors not responding is non-response. And then the reasoning or the undercoverage of them because we didn't get a lot of them. So yeah, it can overlap. Okay, how about some chapter 12? Let's try to do one more chapter here. Let's do some stretch. Who's got stretch? Oh, just do stretch. I feel it. I was doing some pulse this morning. I'm like, I gotta stretch out. You gotta walk around. You have to walk around. It's like stretch out, just relax for a moment, put in the timestamps. That's why I go on walks a lot of times, because if I sit in one spot, your body gets sore. I'm not even kidding. When I went to Texas, I was sitting for like 6 to 8 hours a day. And yeah, check out Movement by Dave, Get Flexy, or Stay Flexy is his motto. Check out that. Really good channel, Movement by Dave. So, yeah, really good channel. He's been working with another YouTuber who's a lot stronger and bigger. He was doing some really cool stuff. He was doing like a hanging catch or something. It was pretty crazy. And the dude's like, how are you doing this? Oh, he was jumping backwards and grabbing the bar backwards. And he had like 40 pounds on him or 50 pounds. He kept doing higher. Oh, your probability time. What's your probability? Stay flexy. Stay flexing. There we go. Here's the possible weather events for Pluto's spring break. Hey, Pluto. Snow, 5%. Okay, what do you do? I know Darius knows. Darius, we've been practicing. You got this. Everyone, what do we got to do? I need everyone to say this. I'm going to write this to start before we even get going on this. What do we do? Ooh, I like that. Use the formula sheet. Yeah, we're going to use the formula sheet, and what else? Write what we know. We're gonna write, yes, Emily and Abby, you got it right there. We're gonna use the formula sheet. We're gonna do that. We're gonna have our formula sheet out. We're gonna write our table right here. We're gonna write E for the event and probability E. So what's the first thing I should write? So what's the first thing I want to write right here? Ooh, we're gonna use a lot of multiplication rule and stuff like that. Snow. And snow has a 0.05 probability. Rain. Just don't even read questions if you get something like this. Just be like, I'm going to write down what I know. And then it makes life easier. Below 40 temps. Oh, below. Ooh, got interesting things right here. I like this, Moira. This is getting interesting. And above 40. Okay, above 40 temp. And I think she means like below 40, at or below. I'm going to put at or below. So that's less than or equal to 40, and this is greater than 40. Yes. There we go. Rain and snow are mute. Ooh. Okay. I get what she's getting at. Okay. That's very important right there for these things right here. Okay. So why did she say rain and snow are mutually exclusive? Formula sheet's huge right here. Why did she say rain and snow are mutually exclusive? Because she's wanting us to do what here? Why did she say rain and snow are mutually exclusive? Because why? Because we can now add them. Right here. By saying they are mutually exclusive, we can add them. That is the requirement for mutually exclusive. So she's saying, and it would be sleet if it was not. What did it cause? Mubot, chill out, man. He's not saying cause. Cause is a bad word. Prove and accept are all their bad words too. So you're saying if it's snowing, it can't also be raining. So a really great example came up in class. Is thunder and playing baseball mutually exclusive? What do you think? This is an example used in class. Is thunder and playing baseball mutually exclusive? And explain why. And then you have to know what mutually exclusive means to be able to explain it. Is thunder and playing baseball mutually exclusive? Yes. If it's thundering, you're not playing baseball. If you're playing baseball, it's not thundering. You could be not playing baseball and not thundering. So people are saying in the chat, it's mutually exclusive because if one thing happens, the other thing can't. Does everyone see the test to do mutually exclusive? You think, is it thundering? Can I also be playing baseball? No, mutually exclusive. So you think, as Moira says right here, that means you can add them. It can't be snowing and raining at the same time. They're mutually exclusive, which she just states it. And so what's the probability for part A? What is the probability for part A? You just add the two together, and it's just probabilities added. The next ones are interesting, and I do agree. I think I know what she's going for. Probability of snow plus probability of rain equals to 0.25. Just add those two right there. What is the probability on one day it's raining and 38 degrees? Raining and 38 degrees. Now, what do you need to assume with these? To solve this problem, must assume what? I think David's done it right there. Dawson's done it. I saw D and I said David. You must assume what? Since we're multiplying, right there, must assume independent. Since we're multiplying right here and we're saying and, we must assume independent. And they kind of are, like, you're not like, man, it's 80 degrees. It'll never rain today. Of course, if it's like 0 degrees outside, it's not going to really rain. It's going to snow or sleet or something like that. So you must assume independence for these. Little bit of it's a good question, but then it comes into a little bit of a problem if you say, well, can I really multiply these? The next one gets into that, which I really like. Looking at the next question. So you just take right here, it says, in 38 degrees. 38 degrees would be this probability here, and you multiply that by rain. So you're just going to take 0.20 times 0.57 equals the probability. So you're going to take times that by 2, move the decimals around. It's going to be 1. Why is my brain not working? It's right. It's going to be 2, right? It's going to be 0.24? No, why can't I math? I can do it. Wait. That times that is that. Is that right? Doesn't seem right. Why can I not math? Oh, because I didn't move the last decimal. I got the 14. There we go. I don't have to move decimals anymore. Logically, is it possible for it to be snowing in 60 degrees? The answer is no. What is the probability temperature will be above or below? So these are what's of this. What is the probability the temperature is above or below 40? Which, it's given right there. So what's the probability it's either at 40 or below? And they're mutually exclusive, so you can just go right here. It's 1. Yeah. 60% of people. Okay, here we go. Very similar again. I might do the... Here we go. Okay, I like this one because we're lowish on time. A study showed that 54% of adults have a cell phone. The concern is that there's not enough cell phones. Okay, towers. So we write out our table, and we do the event of cell phone or no cell phone. And I just wrote the what of it. Say the word. This probability is the what of the other probability. Because you either have a cell phone or you don't have a cell phone. Complement. Fasten that. Technically with an E. Technically with an E. Complement with an I is like great job. Complement with an E is 1 minus the probability of A. Which you can plug in the C right there for probability of cell phone, probability of not cell phone. What is the probability an adult doesn't have a cell phone? Well, we just figured it out. It's the complement. You either have one or you don't. But this is now 5 people, which is a lot like in my Pearson question. I saw this one and I was like, I know how to do these. What is the probability at least one of them has a cell phone? Now, to solve these questions, you have to do the following. Write your sentence. If you've done these problems with us here, you know how to write the sentence. So we're saying either you go into a room and there's 5 people and you say, does anyone have a cell phone? So it'll either be the case that at least one person has a cell phone or what? You go into a room and it's either the case that at least someone has one or what? It's either going to be the case that at least someone has one or no one has one. Does that make sense? These are mutually exclusive. They're also complements, meaning they add up to 1. There's a 46% probability that someone doesn't have a cell phone. So you look at the first person and they what? And these are 5 random people just hanging out together. They say, we don't know each other. We are completely independent of each other. The first person what? You look at them. And they what? When you go to the room. If no one has a cell phone, you look at them and what? You look at the first person. If no one has a cell phone, you look at them and what? The first person what? If no one has a cell phone, the first person what? If no one has a cell phone, the probability of no one having one, you bought in the chat. He's a good Mebot.
Sorry, everybody. I haven't been around much lately, but keep it up. Good work, Tara.
Good Mebot. So the first person doesn't have a cell phone and the second person doesn't have a cell phone. So you're very close right there, Dawson. You did the probability of everybody having a cell phone. So be very careful. So what you need to do, writing it out helps you solve it. The probability of no one having a cell phone is the first person doesn't have one, and the second person doesn't have one, and the third, and the fourth, and the fifth, and the sixth. So there it is, right? Yeah, Kaya's got it. Mm-hmm. Does that make sense? Because you have to use the probability of not having the cell phone. 1 minus the probability, and then you go right here and you change this to a plus. Good job right there. Also, Adeline, you change this to a plus, and then you simply algebra it over to the other side. We did one of these in class day 2. Like, you do a few of these, and they become like, oh, I know how to do that. And sometimes you don't even have to write the sentence if you've done a lot of them. And that abbreviates to, we're just showing the long steps of all the solve. There it is. There's the math. Why do we subtract from 1? Because you're saying the start of this is, if we go to the very start, it's going to be either the case, Cooper, good questions right there. This means one of these must occur. It is either the case that at least someone has a cell phone or no one has a cell phone. One of these things must occur, which means a probability of 1. The next thing we do right here is we simply figure out the probability no one has a cell phone. The first person doesn't have a cell phone, and the second person doesn't have a cell phone, and the third. By saying and, you're assuming that each person is independent, and you can multiply the probabilities together. Make sure that this is a plus now, because or means they're mutually exclusive, which you can't have no one have a cell phone and at least one person have a cell phone. Then we just take this right here, because you can subtract from both sides. So if we showed it the long way, it would be, you would subtract from this side, but if you subtract from one side of an equation, you also have to subtract from the other. That makes that cancel out on that other side. So does that make sense right here? Like, this cancels out because you're subtracting from both sides of the equation. You're subtracting from this side this amount, and then you'd subtract from this side. So then that cancels out. Whoops. Ooh, that says plus. Ooh. Duh. Yes, this won't say. Yeah, sorry, I didn't change that. Ooh, there we go. Thank you. So they cancel out because you subtract from both sides right there. So it says 1 doesn't have it on. Yeah, if you would say the one you solved, at least someone doesn't have. That would be or everyone has. Yeah. The probability everyone has cell phone is 0.54 to the 5th. So this would solve out to at least someone doesn't have. So this is the other solve. If you enter in this solve right here and put in everyone has a cell phone is 0.54 to the 5th. And so if you solve this out right here and algebra it over, you'll get that you just subtract this from the other side because the or becomes a plus because they're mutually exclusive. And does that make sense? So that one's that one. That's at least someone doesn't have. So there's the two solves using the two probabilities. This one is at least someone has a cell phone is the complement of no one has a cell phone. At least someone doesn't have a cell phone is the complement of everyone has a cell phone. Yeah, exactly, Darius. This methodology that I learned from teaching tons of students how to do this. Writing the sentences makes it way easier. And what's the probability that all 5 have cell phones? First one has a cell phone, second one has a cell phone, third one has a cell phone. What's the probability that at least one of them does not have a cell phone? I think we just did this. Yeah, we just did it right there. Yeah. Okay, let's do this next one. You ready? Woo! Got a lot of work. More Magic Co. is a company that manufactures ships magic kits to kids. Check out Amazing Randy. Shout outs. Just going to give him a huge shout out because we're finishing off here. But if you've never heard of Amazing Randy, sadly, he passed away in 2020. It feels like, gosh, I felt like he passed away more recently. He passed away in 92. And really great magician right there. Just a lot of different things he did from Canada. But the Amazing Randy right there, really cool stuff. Check out some of his work if you want to see cool magic stuff. Or he does a lot of debunking of different things, but really fun stuff. So magic right there. A study conducted by the Consumer Services showed that 7% of the kits arrived with missing or damaged parts. The company decides to randomly select 4 orders. So we write out our table to start. Here is our table to start. We have the event and probability of the event. What are the 2 events? What are the 2 events? Last question for office hours. What's the 2 events? What is the 2 events? Remember, don't look at the questions to start. Write down what you know. Yep, we got defective. We'll say defective right here. and not defective. So it's either defective or not defective. Like we've got like messed up products. So 7% of our products, that's a 0. My numbers are so bad. I've only been writing numbers my whole life. As a punishment, we had to like write sentences as a kid. And I would just be like, scribble, 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 scribble. Probably my sentences are so bad. Right. Didn't get punished that much. What is the probability all 4 customers received unharmed kits? Pretty easy. What's the probability? Tara, good work and good seeing you. What's the probability all 4 customers don't get damaged kits? The first doesn't get a damaged kit, and the second doesn't get a damaged kit, and third and the fourth, or the 4 we sample. What's the probability the 4 we sample are not damaged kits? The first is not damaged, and the second's not damaged, and the third's not damaged, and the fourth's not damaged. You got it, Dawson, right there. What did you assume to do this? Don't type it in the chat, though. What did you assume to do this? Okay, to solve that math, right? Oh, God, there's my keyboard. To solve this math, what did you just do? Here's a hint. If you don't know the answer, look at the formula sheet. You go to the formula sheet and you're like, wait a minute, I was just multiplying things together. Would you look at that right there? Independence. So that would mean each kit would not impact the other kit being defective or not. So these are not like products that are made next to each other, I would say. It's like you grab like 4 random products off the shelves to see if they're defective. And each kit would have to be randomly selected. So that to the 4th power. What's the probability all 4 customers received kits with damaged or missing parts? You can do it the long way. And once again, we're doing the independence rule right here. I'm running out of room. Yep, with me, I'm already past it. And there we go. And next one. What is the probability at least one of the kits contains missing parts? So it would be the probability at least one defective, or what? Either at least one is defective or what? Finish my sentence. Either at least one kit is defective or what? Either at least one kit is defective or what? Or what? It's either the case that at least one of the kits will be defective, like 2 could be defective, 3 could be defective, or none. Great job, Abby. None are defective. So we actually figured out the probability that none are defective. So we're just literally going to take that probability right here, start plugging it in, because we already figured out from an earlier problem that the probability that none are defective is this. And then we just change this to a plus because those are disjoint. You can't have at least one defective and none defective. We drop in the math, and we go right here. There you go. There is the probability at least one is defective. What's the probability at least one of the kits? What's the probability at least one of the kits arrived completely undamaged? So that would be either, it's either the case, at least one is not damaged, or what? At least one is not damaged, or what? It's either that at least one is not damaged, or what? It's like, man, at least one of those kits won't be damaged, or they'll what? Either at least one. I'm like, or what? Oh, like John the Bravo. At least one is not damaged, or what? Or they are what? At least one is not damaged out of the 4, or what? What's the other side of this? Either at least one is not damaged, or what? They're all damaged, yep. So we figured out the probability of all damaged because the probability of damage is 0.07. So the probability of all damaged is going to be this. Oop, 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 oop. It's 4 kits. Yeah. All damaged. No. Either at least one is not damaged or they're all damaged. Because at least one not damaged means it could be like 1 is not damaged, 2 is not damaged, 3 is not damaged, 4 is not damaged. It wouldn't include that they're all damaged. So either at least one is not damaged or they're all damaged. And really good review from Moira right here. Yeah, in chapter 13-14, we did a lot of this yesterday. Should be clumpy and cone shape. No, they should be random. They should be random. Oh, man, I want to do more. Okay, should we speed run the true falses right here? Who wants to speed run the true false? Who's here and got the energy to speed run with me? And then I got to go out to in-person office hours because they're technically going on right now. But I want to speed run some true falses if you're with me. I need some energy. Erica wants to do this? Okay. I might speak quickly here. But we're going to do Moira's true falses. I'm going to try to explain these quickly. So you got a Morbin. People don't even know about this. I need some Morbs in the chat. We got a Morbin right here. You ready? True or false? Residuals add up to 0. That is a fact. Residuals add up to 0 because the line goes to the center of the data and residuals kind of go randomly around it, or they should. The conditions for the sample means are for the same for the sample proportion. That is false. It goes random, 10%, and then you have to pause. You put those pause in the chat. That's not a condition, but you pause and you do either success failure or you do large enough n based on if it's proportions, it's success failure, and sample means is large enough n. Also, a fun fact, you do not need to check conditions to calculate p hat or y bar. Checking conditions are to see if the data follows the what. Checking conditions, say it in the chat, is not to calculate p hat. It's not to calculate y bar. Checking conditions is to do what? Checking conditions is to do what? To see if what? I hate getting random calls. Checking conditions to see if the data follows the normal. If you pass the random 10% and success failure for categorical data, you can use it to describe the normal curve to describe your data. A consistent sample size does not matter when comparing sample proportions. One can have a sample size of 6 and the other can have a sample size of 12. I don't know what this is getting at. I've never written a test question like this. Yeah, I'd say sure. Sure. It's just you can get the proportion. Yeah, I mean, you can find the proportion from 6 and the proportion from 12. Yeah, you can calculate because it's x over n equals p hat. Someone left a message. Sample proportions are for categorical. Sample means are for quantitative. True. That's just a fact. Event A is the temperature being 70 degrees. Tomorrow, event B is snowing. That is false because we know that snow depends on the weather. So snow depends on the weather, so they're not independent. Two events that are independent must have equal probability of occurring. That is false because you could say winning the lottery. So probability of lottery win is something ridiculously tiny. And the probability of snow is in January something like 10%. They don't have to be equal or whatever. It's easier to add up probabilities when they're equally likely. That's easier when it's to do, and we're not adding right there. We're doing independence. Event A is like in baseball. Event B is like in football. They're independent. I would say false because it means you like sports. I don't like sports. I like baseball. Well, I don't know. I like sports as a baseline of what people like for sports. It was so much fun. Thank you to UT Baseball. I really enjoyed it. But I'm not a big sports guy, but I was psyched. And my wife's like, "You don't even like sports." I was like, "But it's the first pitch." She's like, "But you don't like sports." I'm like, "But it's the first pitch." I went to baseball games as a kid. When taking this into answer 7, it's because if you like baseball, you probably like sports. So liking sports is going to increase the probability of liking another sport. It's not like you must like football, but people who like sports typically like other sports. So if you know someone hates baseball, soccer, football, and you ask them, what about hockey? And they're like, yeah, I hate hockey too. Because your like of a certain sport probably depends on liking other sports. Now, it doesn't mean you will like a sport. It just means people who like one sport are probably more likely to not like another sport. It's not independent. We're taking the square root of r squared. You need to check its direction of the graph. Exactly. Because if you have r squared right here is equal to 0.36, what is the value of r? Who can do this one? This is true. What is the value of r for this question? R squared is 0.36, so what is the r? And you have to look at the visualization to say the answer. Nice job, Dawson. Yep, check the sign, because it's negative, because it goes down. A sample size of 25 would satisfy a large enough condition if it's heavily skewed. No. False, need 100. You need 100 for that. For the regression equation, because the more skewed it is, the larger it needs to be. For the regression equation, B0, no, that's reverse. It's flip-flop. B0 is the intercept, B1 is the slope. For each 1 unit increase is the slope, and B0 is when x is equal to 0, so that's the intercept. Statistical significance for a linear model means that there is reasonable evidence to say that the linear relationship is unlikely by random chance. Yeah, it's basically true. Yep. The sample frame is everyone who ended up being sampled. That's false. It's everyone we had access to sample. The sample space is all possible outcomes, which is a different concept. That's chapter 12 is sample space. Residual plots should be clumpy and cone shaped. No, they should be random. A good residual plot shows no patterns. This is a good residual plot. Looks pretty darn random. And a bad residual plot is going to have weirdness or clumps or show patterns. That's bad. It's a bad residual plot. And there's a good residual plot. Nice. They should be random. With that, we're going to save this right here. We did that in just like 5 minutes. Stay tuned. Ask questions. Check out the review page. You're welcome. Are we able to go back and look at our Canvas content quizzes? I think the ones you've done. And also, they're in the class videos. So check out the class videos, or not the class videos, the office hours videos, because I do a lot of the Canvas content. And just pause the video, look at the questions, try to solve them, see if you get them. Bye for now, everyone. Bye.